Um, Hi everyone, my name is Shengyao Zhuang from CSIRO Australia. Today I'm presenting our SIGIR full paper leveraging LLMs for unsupervised dense retrieval selection. First, let me describe what is dense retrieval selection. I assume you guys here are all familiar with dense retrieval. Use two sentences to describe is you use a embedding model to encode all the documents in the collection into embedding. You put them in the vector database. At the query time, you also encode the query into vectors, and then you search in this database to find the most relevant documents. So dense retrieval selection task is that given a dense like embedding model pool, and the task is to select the most, the best performed dense retrieval from the pool that has the best retrieval performance on your target collection. So that is the task we started in this paper. This is actually a very easy task if you have testing data on your target collection. So like if you have testing query and you know which documents are relevant to this query, then you can simply just evaluate all the dense retrievers in the model pool and to know which one is the best, right? And then you just select that. Sounds very easy. But the challenges here, we argue that this is not always the case. Like, it's not that easy to have this testing data. Sometimes it's expensive, sometimes it's even impossible. For example, in the email search scenario, it's not ethical to hire human annotators to judge all the user emails to create this testing set, right? This is a challenge. An easy solution to this is that you can use some open source testing data or to validate all the dense retriever in your pool. For example, here you can use MS Marco to select to rank the dense retrievers, and then you know which one is the best, at least on MS Marco. Here actually I list some dense retrievers. These dense retrievers are trained on MS Marco. So in this case, it's kind of in-domain performance. I cannot move my. Okay. So what's the challenge here? Actually, our community identified that there is a supervised and zero-shot effectiveness trade-off. So this is studied by Waterloo University. So the x-axis here I show is the performance on MS Marco. The y-axis here is a beer data set, which is like a different domain, and you find if you dense retriever overfits MS Marco, you get low performance on other domains. So that's the challenge. It's kind of dangerous to only rely on MS Marco. Yep. Another good example to show you the significance of the problem is this massive text embedding benchmark leaderboard. So in this leaderboard, lots of universities, research institutions, including like OpenAI, submit their embedding models there, and this benchmark has actually they use beer data set to evaluate the retrieval performance of these dense retriever models or embedding models. So I show you the ranking by last month and ranked by the performance of average retrieval performance on beer dataset. However, if you rank them by track COVID dataset, which is medical domain, you will find a completely different ranking. The top one performed dense retriever is not even in the top 10 of the list if you rank by track COVID. So again, this is like, really the problem is dataset specific or domain specific. Here I show you the best dense retriever, open source dense retriever. On the leaderboard, when I conduct this study, I show you the performance on beer dataset. And then here I show you if you select the best dense retriever according to each dataset, you will find most of the cases the best average performed dense retriever is not always the best for some of the datasets. Again, these two, we know which one is the best according to average or the best according to each data set. It's because we have this testing data. This benchmark provides you testing data. And then if you select by MS Marco, you get a very bad result, right? You rely on, retrieval performance on mass Markov, you will select one bad dense retriever. And then if you use the method proposed in our paper, we call LLMs, you actually can select a very good one. And actually, we can achieve slightly higher average score than the best dense retriever. And again, I want to emphasize that here is our method does not use any testing data. What we have is only the target corpus. So everything is zero shot. How we did this? We actually extensively reach LLMs, surprise, for this task. But why large language models? So there are a bunch of works have shown that LLMs are good at synthetic data generation for information retrieval, and people are actually using this synthetic data to train dense retrievers. And LLMs are also very good annotators, AI annotators to give you relevance judgment. So you can just generate judgments using LLM, evaluate dense retriever, and probably you can get good selection result. Also, LLMs are good rankers. Many papers using LLM to do zero-shot ranking. So all in all, we think LLM is a good idea for this task. So we propose LLM, large language model assessed retrieval model ranking or selection. Okay, so next time describe our LLM pipeline step by step. So again, we assume we only have collection, documents, even no query, no judgments. So the first step, we actually sample a subset because corpus is usually huge. We sample a subset, small subset of that randomly. And then the first step is to generate some queries. We simply use instruction tune the LLM, give the prompt, generate a relevant passage, generate relevant question for these sample documents. And actually, at this point, you can already do the dense retriever ranking, right? You can assume this generate query and document pairs are relevant. So you have this kind of very shallow relevance pool, judgment pool, and you just do the selection based on that. But we think this is not enough because in this way, each query only have one relevant document, but we know a query probably can have more relevant document. So this shallow judgment is not good. So the next step, we propose to create a reference ranking. So what we did is we issue the generated query to each dense retriever in your model pool. So you will get a ranking for each dense retriever for each query. And then we use reciprocal fusion to fuse these rankings to get a reference list. That's what we call a gold ranking. Then how you do the selection with this gold ranking is you can use some ranking matrix, the similarity matrix like RBO to compare the ranking of each dense retriever against this gold ranking reference list, and then you just assume more similar ranking better. So you can rank dense retriever in this way. And then to further enhance the selection performance, we issue this, we use LLM again by giving the ranking to LLM. And we actually did two paths. The first path is we sending this reference list to LLM and asking LLM to judge the documents there. So here we use this Frank-Graham relevance prompt proposed by Zhuang, know me, a different Zhuang from Google. So the instruction is judge the document whether they are highly relevant, somewhat relevant, or not relevant, and we only keep the highly relevant. This is suggested by this paper. So you can create judgments, and then you can rank dense retrievers by these pseudo judgments. The other path is that we also use LLM to rank this reference list to get an even enhanced reference list. So we use the set-wise prompting, which is also proposed by Zhuang here, the correct Zhuang. But actually, the other Zhuang is also one of the authors. So, and this is accepted this year again. Like I gave a talk about this paper yesterday, and so I don't want to give too much details here. You can watch the recording. The idea is, you can use this prompt to rank documents, and hopefully your LLM can give you an enhanced ranking. And again, you use RBO to rank the dense retrievers ranking against this enhanced reference list. And the final step is just fuse this dense retrieval ranking you get from the two paths to use the fusion again. So for the experimental setup, we use beer dataset and 47 SOTA dense retrieval from the leaderboard back that time, and then we use Flantify as of LM backbone. So that's this. For evaluation, we care about the model we selected, the retrieval performance of the model we predicted against the ground truth dense retriever. So we calculate this NDCJ turn difference to indicate, so the score lower is better if you select the ground truth best, meaning the difference is 0, right? So 0 is the best. So here I show you big table of results. I don't want to give too much details about baselines, but you see if you select by MS Markov method, you get pretty bad result. Here is bunch of QPP, query performance prediction baselines. They are also, most of them are really bad. The best one is using Fusion to do the QPP. And our method achieved generally very good performance. So on average, only 2 NDCG lower than the ground truth best. And for 2 datasets, we actually predicted the best dense retriever. And many of them are very small difference. And I think they are second best or third best. So that's good. And as I mentioned, there are few points in the pipeline that you can select dense retrievers, right? So here I show you ablation study. At each, the points can, each points down in the pipeline can improve over the previous points. Of course, there is a trade-off here. The full pipeline is kind of expensive. If you want to quickly have a dirty result, then actually the first point is pretty quick, and it's already much better than lots of baselines. Final slide. We also have a demo about this method. We try to build a platform allows you to submit your corpus, upload to the platform, and then we run our pipeline at the back end to suggest to you which open source dense retriever you should select. And you can also download the generated queries and the judgments. Probably we can also provide rankings later, not now. So you can do evaluation by your own self. And I think we'll open source the code as well. And that's all. Thank you.